All right, apologies everyone for the delay, but here we are now. Sorry for the delay. Just had to wrap something up that was very time sensitive. It was related to something involved in this course. But anyway, with that, today we're going to be discussing JUnit testing. We're then going to briefly discuss the software development lifecycle. In so much as we have time for. Part of JUnit testing, we'll be discussing testing strategies. That's, no offense, that's a little bit, that can be taken so many different ways. Please, yeah. Anyway, um, to that end, just some notes. Homework 1 due tonight. Quiz 3 due tonight. Similarly, homework 2 is released today. Homework 2 does include JUnit testing. So you do need to pay attention today to be able to do all of homework 2. Homework 2, your homework submission will not be accepted without JUnit tests. WebCat will refuse to run your program against our tests until all of your tests pass. And you have a sufficient number of them. So we'll talk about that today. Finally, the exam is still Friday. It will be noon to 11:59 p.m. We'll talk more about the exam on Thursday. Exam instead of class, so there won't be a lecture that day. Everything that we cover between now and Thursday, up to and including Thursday, will be on the exam. Any questions? And again, I apologize for the delayed start here. Alright, so last time we left off talking about testing. We left off talking about how it's not always obvious when you look at a piece of code whether or not that code works. For example, this piece of code actually does work, even though it doesn't look like a max function. And so the way that we judge our code is we design a test case. Now, to be clear, we test not to prove our code works. That is not the primary purpose of testing. The primary purpose of testing is to find bugs. We are looking for bugs. We're trying to find them. We're not trying to prove our code works. Because if you're trying to prove your code works, you're going to test with a mindset of, well, I hope this works. And then once you get test pass, you're going to move on. No, we're actively digging our hands into the dirt of our code and looking for bugs. Both of these situations in this comic are bad. Neither of these are good. We don't want to not understand our code. To be clear, program testing can show the presence of bugs, but it cannot show their absence. So the goal of testing is to find bugs. It's not to prove the code works. That's the mindset you want to have. It allows us, so testing, you may think, well, if we can't ever find every bug guaranteed, then what's the goal of testing? Testing removes uncertainty. An untested system, we have no idea whether or not it works. By testing it and by not finding bugs, we are more certain it works, up to a point of maximum certainty, but in the universe, there is no maximum certainty. For example, right now, I think that I'm sitting at my computer in my house drinking a soda. I think that I'm bald and I think I wear glasses. It's possible that I am, albeit unlikely, that I am delusional about one of those things, but I don't believe that I am. You can never be absolutely certain about everything. Sorry, this turned into a philosophy class. But we are going to try to be maximally certain here, as certain as we can reasonably be, that we have done our best effort to find bugs. Recognizing that our maximal certainty, especially in computer science, is very poor. It's very, very uncertain. So to design tests, we start by designing testing scenarios. And a testing scenario is three things. It is, because remember, what is testing? Let's go back to our definition. Testing is executing, running our code, running a piece of software with the intention of finding bugs. So how do we execute our system? Well, we execute our system by designing a testing scenario, and that scenario is we have an input, whether that's inputs to a function or whether that is the state of a system. For example, the state of certain variables, and we'll get to examples of that later. Or whether that is any other features. So some input, then we have an expected output. This is what we think should happen, including side effects. And we've talked about side effects before. Remember, what a function returns is one thing, and the side effects are the other. So for example, the function Pez dispenser load. It is a void function. It returns nothing, but it has the side effect of filling a Pez dispenser with candy. So side effects are anything not directly related to return value. That is part of the output as well. And then finally, we have an actual output, what the system actually does. And a test passes when the expected and the actual match. And a test fails when the expected and the actual do not match. And a test failing is often, though not always, indicative of a bug. And we'll get to examples of that in a second. So that is a key definitional term. A testing scenario or a test case is three things: input, expected output, actual output. You need all three of those for a test. Are there any questions so far? I just realized the title of this stream is wrong. There we go. Any questions? All right. So now, let's take an example. Also, course is spelled wrong. I can fix. You know, that's not being very nice. I'm joking. There we go. Thank you. Okay. You will get used to the fact that I have typos. I do work really hard to fix them on exams, though. All right. So, with that, here is a testing scenario. Pardon me. So I have this max code, which remember is this code we used earlier. It has a bug. We know it has a bug. We know this should be returned C. But for the sake of this class, I'm going to intentionally leave this bug in place. Return A. So let's say I have these arguments. I decide the input is 3, 2, 1. Well, my expected output is the maximum of the 3. So I'm going to say that my expected output is 3. So now let's go ahead and let's, and I'm going to real quick just create a new Java project for today. 0623 testing. And then I already have my my files downloaded, so I'm just going to copy them over. And then real quick, I'm going to go to this functions file, and I'm testing this function which has this bug. And I know you can't see this, so I will, there we go. Should be C. And I'm just going to do a quick little main method test. Public static void main string args. My input, int A equals 3, int B equals 2, int C equals 1, and then I'm going to get int expected equals 3, expected output, and then int actual, this is from running the code, is going to be max A, B, C. Actual output system.out.println expected equals actual. And as we said before, this code has a bug. So this test should fail, right? Wait a minute, what? It's printing true? Huh. Well, why is that happening? Why is it that when I run this test, the expect and the actual match, therefore the test passes, but I thought we had a bug? How is it that this test is passing if we have a bug? Does anyone know the answer to that? If we have a bug in our code, how is it that the expect and the actual are matching? It's because... Exactly. Two of you have gotten it. It's because the bug is on line 10. And the simple fact is, if I trace my code, you'll see that if A greater than B, well, that's true. If A greater than C, well, that's true. Return A, and I'm done. I never get to line 10. I never execute this bug. And so the key takeaway here is a test passing does not mean there are no bugs. Very important. Just because a test passes does not mean you do not have bugs. Testing is like potato chips. Both have contributed to my stress and poor health, and one is not enough. One is not enough. We need to test our problem on multiple inputs. This is why on homework 1 we require you to write 2 tests, not just one. Because your code may work in one situation and fail in another just because of a problem that you didn't consider. And so it is not enough to just write one test. So we need to consider multiple scenarios. And to do this, let's go ahead and try another test. Let's try this test. Instead of 3, 2, 1, let's do 1, 2, 3. So I'm going to just copy this, and I'm going to delete, since the variables already exist, I'm just going to delete the declarations. I'm just going to change them. So let's say, for example, I did 1, 2, and 3. My expected output is still 3. My actual is still max ABC. But now does expected equal actual? In this case, it does not. I get false. In this case, I get false. They are not equal to each other. That means that this test fails. However, so this may imply something. You may be thinking now, okay, well, if this test fails, that means that there must be a bug in the code that this test goes over, and because this test passes, it means that the 3 lines there can't be any bugs here. You might be thinking that because this first test passes, all the lines of code executed by the first test have no bugs. And because this test fails, it must be executing a buggy line of code. Therefore, you could extrapolate and say, okay, if a test passes, there are no bugs in the lines of code it executes. It's a reasonable assumption, but it's wrong. Let's design a third test. A, B, and C are all equal to 3. The expected is therefore 3. We get our actual, and it also prints true. So it passes. The key here is that both of these two tests, test case 2 and 3, both of these, it's false, it goes to the else. This is false, it goes to the else. And both execute this line of code. But one test passes and the other fails. So just because a test executes a line of code and doesn't fail does not mean there are no bugs. That's important to understand. Just because we design a test that executes a line of code and it passes, it does not mean that line of code is correct. It just means that our test may have been designed in such a way that it wouldn't catch the bug. And that's what happened, and that's why this test fails and this test passes even though they execute exactly the same lines of code. This is why it's difficult to be certain that your code works, and you want to test vigorously. So far, we've been talking about how to design tests as a series of test cases. Let me fix this real quick. I had a bit of a alignment issue here. So from there, what we have been talking about is main method testing, but main method testing really is not ideal. Because notice that now I have all these tests in main, but what if I need main to actually do something? What if I need my main method to actually call functions in a certain order for the program to run? Now, if I need my main method to do something, I have to comment out all of my tests. And then I can write my code. But now if I need to come back to testing, well, I need to uncomment all of my tests, comment out all the code that does stuff, etc. This is not a great place to have your tests long term. So instead, we can write our tests in a separate class. And we're going to write a very special class. Give me 1 second. We're going to write a very special class called a JUnit test case class. And here's how we do that. I'm going to right-click on my source folder. I'm going to go to New, and instead of class, I'm going to come all the way down here to JUnit test case. Now, this is very important. Do not type a name and hit OK yet. Because there's 3 different forms of JUnit that Eclipse supports. We will be using JUnit 4. JUnit 4 is more established. It's more widely utilized at the moment. JUnit Jupyter is gaining popularity, but JUnit 4 is still more popular. WebCat only supports JUnit 4. So your test cases on this bar, you must pick JUnit 4. By default, it will prompt JUnit Jupyter. You need to change that to JUnit 4. You need to absolutely make sure this is JUnit 4, or when you submit to WebCat, it won't work. From there, we give our class, our test case, a name. Say functions.test, or functions not .test, excuse me. Just functions test, no dot. I'm going to finish, and then from there, it's going to pop up this window, which says JUnit 4 is not on build path. Do you want to add it? Always hit OK if you see this window. From here, we can now start defining our test cases, not in the main method, but instead over here. So I'm going to start by taking this same test case I wrote earlier. I'm going to have to make some changes to it, but for now, let's get started. And inside of this test method, I'm going to change the name of this method to say test ascending. This is a test method. It must be public, it must be void, and there must be this @test above it. You will only ever see this @test in a JUnit test case class. You cannot put this into any class. It must be a JUnit test case class. You'll notice at the top, we have a couple import statements up here. Leave these alone, but they do need to be there. Your test methods must be public, must be void, and must have no arguments. From there, to get my actual output, as I brought in my inputs here, I would say int actual. And remember how we talked about how you can run static methods in another file by referencing the class name? So, functions, because I'm referencing public class functions. Well, yeah, I'm missing some letters there. Or no, I just got them out of order. Anyway. Functions dot max A, B, and C. Now from here, when you looked at my main test, I used system.out.println expected equals actual. Here's the thing about JUnit. It actually doesn't require you to read output, because when I'm running these tests in main, I have to look at my output, and I have to say, okay, true, false, true. You don't have to do this with JUnit. There's a separate method. And that method is assert equals expected actual. This method asserts that the expected must equal the actual. If it is, then the test proceeds. If it is not, then the test fails immediately. Further, you can add to JUnit an error message. Something like max function failed with ascending arguments. In your JUnit test for this class, for this homework, you are required to write some kind of meaningful error message. And then it's always expected and then actual. We'll talk about why in a second. So this is our first JUnit test. Notice there's no print statement, there's no return statement. We just have this assert. From there, I can run this test, and you'll notice that up here in the left appears this little box. And it shows me my test ascending. It has a green check, which means my test passed. And if you look, it says 1 out of 1. That means I ran one test, and one test passed. From there, we can do another test fairly simply. Make this one descending arguments. Make this 1, 2, and 3. I don't need to change my expected. It's still 3. My actual, ABC, is just 1, 2, 3, so I can leave it as is. And then I change this to say descending arguments. Very similar test, but I changed the input. Let's run this test, and we get this red box. This red box means a test failed. Specifically, the test that failed was test descending. And if you look at this failure trace, and it's hard to see, let me see if I can... I'm trying to see if I can enhance here. There we go. You'll see that the error message says, max function failed with descending arguments. Expected 3, but was 1. And that's for this test descending. What happened? Oh, I'm gonna have to... Oh boy. Hang on. Blowing up the window may have been a mistake. Okay. We're back. So what it meant was the expected and the actual were not equal to each other, and because the expected and the actual were not equal to each other, the test failed. What if you have complicated code, one with high-level math where you don't actually know the outcome? You're going to have to work one of those, you're going to have to work out your test cases. So you are going to need to take the time and actually work out what the expected should be for some set of test cases. You just have to do that. You cannot just run your program and look at the number and guess whether or not that works. You can design your test case to be easy to calculate, but you are going to have to design test cases. You cannot just eyeball it. Doesn't work. You're going to have to work it out by hand in some cases. Also, if you break your problem up into smaller problems, if you break your problem up into smaller problems, you might be able to test each individual step more easily. What does 2 out of 2 mean? This means that we ran 2 tests and 2 completed, but one of those tests failed. So there's an error means the test crashed. A failure means the test ended, but it ended in failure. And so if our test fails, that indicates to us that there is a bug. Maybe. It's possible there's a problem with the test. We'll talk about that in a second. So now I come back and, oh look, silly me. I forgot to fix this bug that we already knew about in Max. Namely, we knew this should be C. So I fixed it. I save. I rerun my test. And now you'll notice all the tests pass. So this is what you're looking for. You're looking for every test to pass. And it's because we fixed that bug. Are there any questions about this so far? And I wish I could blow the size of this text up, but I can't. Is there a good way to run one test at a time without commenting out? No, but here's the thing. You don't need to worry about running one test at a time. You can just run all the tests, see which ones fail, try to fix those bugs, and then rerun all the tests. Because these tests run separately. Like, notice, these tests don't even run in order, necessarily. In this case, if you actually look, test descending finished before test ascending. It runs them in an unpredictable order. I don't want to say random, but an unpredictable order. So the tests don't interlap with each other. When would you use this method instead of using a debugger? You need to use tests to find bugs. The debugger is used to help you identify why a bug occurred. The debugger does not tell you when a test fails. The debugger is used after you know there is a bug. The test cases are designed to help you find when there is a bug. So it's 2 different problems. Knowing that there is a bug is the first step. The second step is then figuring it out and fixing the bug. But you can't do the second step until you know a bug exists. The test cases are designed to help you find that there is a bug. And also, your test cases can help you narrow down where that bug occurs so you can more precisely use the debugger. So often what I do when a test fails is then I use the debugger on my test. I actually step through on the test. I copy off in the test code into main, and then I step through that test and see why it's failing that way. Can you incorporate a scanner in the test to make the test soft-coded? No. No, your test should be hard coded. If you want, so the key is your test should be hard coded, but you just have a bunch of them, so you get a broad coverage. And we'll talk later today about how to select what inputs to test. But you should never use a scanner. You should never try to solicit user input in one of these tests unless it's completely unavoidable, and in this case it's not. You just, if I want to test different cases, I just write more tests. Because here's the thing. Now that I have these tests over here, and I can add my last test that we did. Test equal inputs. And make all of these 3. And the expected is 3. And I run this. Now that I have all 3 of my tests in this JUnit file, I no longer need these tests in main. I don't need them here at all. And so if my main function needs to do something, it's free to do it now. And if I find I need more test cases, well, I just add them to functions test. But now I can run functions separate from testing functions. So for instance, I might have some kind of program that's, system.out.println, enter 3 numbers. Scanner SC equals new scanner system.in. I need to import sc.next int. No, not has next int, just next int. sc.nextInt, I could say something like int a equals that. And then something like system.out.println, the largest number you entered was max A, B, C. So this could be the program in main. This could be what I intend the program to do. So the user runs it, and they, hang on. Oh, forgot a semicolon. The user runs it, and then they enter 3 numbers, 25, 14, 17. The largest number you entered was 25. This could be the intended use of the program, but notice that by running this program, I'm not running my tests. And similarly, by running my tests, I don't run the program. So I separate testing the program from the application that the user sees. I make them 2 different things. And that's actually intended. Now, to be clear, just because a test fails doesn't mean there's a bug. And this is where it can get a bit weird. For example, I could have testing errors. I don't know why I have these capitalized. Testing errors. For example, I could write a test incorrectly where my input is 4, 5, 6, but I incorrectly state the actual output is 4. But because I have that bug, assuming I still had that bug, this test would pass erroneously. This is called a false negative. A false negative is when a test passes, which indicates there is no bug, when there actually is a bug. My test is incorrectly constructed. Similarly, I could incorrectly construct my test such that the test fails when it should not. And that's because my expected input is incorrect. Can you run a JUnit test on a non-static method? Yes, you can, and we'll do that in a second. And so, a false positive is when your code indicates the test fails when it shouldn't. Now, that may seem strange to say it's a false negative when it passes and it's a false positive when it fails, but understand that our goal is to find bugs. Pass indicates there are no bugs. That's why it's a false negative. Fail indicates there are bugs. That's why it's a false positive. These two tests, the reason they produce erroneous output is because these two tests are unsound. Unsound. And a sound test is a test that correctly matches the specification. By that I mean, the specification is, here is what this function should do. If the test is in line with that specification, it is sound. However, if that test is not in line, it is unsound. These two tests are unsound because it's saying the max of 4, 5, 6 is 4. That's incorrect. That doesn't make sense. That doesn't match the specification. I can make the test sound by saying it should be 6, and now the test would be sound. So we want to take time when a test fails. Our first step should not be to look for a bug. Our first step should be make sure the test is sound. To that end, all the tests on Homework 2 are sound. I know they're sound. I've tested them thoroughly. So don't assume that if a test fails when you submit to WebCat, it's not because the test is wrong. Any questions about sound or unsound tests? All right, so now let's take a minute and let's talk about how we would test an object. It's important to understand how we would test an object. So let's say, for example, I had our good old friend Pez Dispenser. And here I have this class Pez Dispenser. And I actually do have some bugs in it. I uploaded a Pez Dispenser for today that is intentionally buggy because we're going to find them. From there, I can design test cases. And I'm going to just comment all these out for now, take them off the screen. Because these are the tests we're going to end up with, but we're not there yet. And my question to you is, how could we test in Pez Dispenser the function load? After all, the function load is void. So how can we verify that that's working correctly? Well, first we create a test, public void load test. And then we need a Pez Dispenser. So we create a Pez Dispenser to test with. Let's say Pez Dispenser, new Pez Dispenser. Let's say this is a Yoshi. Yoshi the dinosaur from Super Mario World. It has a green sleeve. And it has a capacity 12. Oh, wait, no, sorry. We only have 2 because the capacity is static. So we create a Pez Dispenser. Oh, that's right. I had this one I have a color for. Color.white. Sorry, this is the color class in Java. I'm not expecting you to know it. Just know that this is a way to represent colors. Sorry, it's not white, it's green. From there, I have my Pez Dispenser. If I want to test the load function, I need to call load on this Pez Dispenser. So I do test.load. That's because load is not a static function. Load is a instance method. So it acts on an instance. So I am loading my test Pez Dispenser. From there, how do I know if this works? Because after all, this is void. This doesn't return anything. So how can I check if load worked if this doesn't return anything? How can I check if load worked? Anyone? What changes after I call load? Let's take a look at our Pez Dispenser class. What should change? Because the point of calling load is to change one of these fields, right? The number of candies in the Pez dispenser should change, right? Num candies. So, and now since it's private, I have this getter. And so, I can test whether or not load worked by saying int expected candies equals 12, because it should be loaded to capacity. And then assert equals, it's going to be the error message is load didn't load the correct number of candies. My expected is and I'm gonna just hit enter here. My expected is expected candies, and my actual is test.get num candies. So this is how I can test it. Let's go ahead and run this test. And it passes. So load is correctly loading the correct number of candies. But we're not done. Yes, load should change the number of candies, but it should not change anything else. That's important. And if you look, you should notice there's a problem with my load function. Someone tell me if they see that very subtle bug that I have. Right? There's clearly no reason that loading the Pez dispenser should change the color of the sleeve. That doesn't make any sense. Why would I put this here? Well, I put it here as just an example of it's not enough to test, when testing objects, things that should change. You also have to test things that should not change. So, in addition to testing what should change, we need to test what should not change. We need to make sure side effects we don't intend to happen. And so, assert equals load change the sleeve color when it very much should not. The expected sleeve color expected color equals color.green, because that's the color that we started with up here. So and then expected color test.get sleeve color. I want to make sure that that also does not change. So I save, I run, and oh look, my test failed. Well, silly me, look at this bug in my code. How could I ever do something so stupid? So I fix this bug, I remove that line of code, I save, pardon me, I then rerun my tests, and now you'll notice that my test passes. Should we write all the fields in one test? You should include all the fields that do not change. Now, there is, I want to be clear, there is a paradigm which I am not expecting. I am not expecting you to do what I'm about to say. There is a paradigm called one test per test method. And in that paradigm, what you would be expected to do is something like this. Load test count and load test color. And in this case, you would be expected to do something like this. The same test, but check a different output in each test. This is a paradigm. So if someone ever tells you they expect one test per method, this is what you would have to do. I'm not expecting you to do this. I'm very, very much not expecting you to do this. But I am expecting you to test all of the fields that could change. Notice I do not test the fields that are final. And that's because I don't need to test the fields that are final, because the fields that are final can't change anyway. So I don't bother with it. Make sense? So then similarly, the way I could test dispense, I would have two different ways of testing it. And I'm just going to copy these. Give me 1 second. Because I have two different times that dispense does a meaningful thing. I could test dispense when there are 0 candies. So I immediately call dispense. Remember that dispense is a Boolean function. It returns true if there is a candy. It returns false if there is no candy. So I test and I do assert false. Assert false is a method like assert equals. Only it says that rather than two things should be equal, it's saying that this should return false. So pd.dispense should return false because I create a Pez dispenser that I never load. So it's empty, I dispense, nothing happens. Then I have a separate test for dispense not empty. This one creates the Pez dispenser, but the difference is before we do testing, we load it. And then dispense now should return true. So we say assert true. Assert equals takes in 3 arguments: an error message, an expected value, and an actual value. Assert true and assert false only take in 2: an error message and something that results in a Boolean. Why would the expected value be placed in front of the actual value? Because that's the paradigm. The paradigm is expected before actual. And I'll show you why. Let's say that I swap these. Let me do this. Let me do expected color. Let's say I get these out of order. And I'm going to reintroduce my bug. It turns out that it makes the error message misleading. So this will fail. But when I run it, you'll notice the test fails. And if I zoom in on the error message, you'll see that expected Java AWT color R255, which this is, by the way, this is colors in Java RGB, red, green, blue. So red 255, green 0, blue 0 is the color red. Red 0, green 255, blue 0 is the color green. So it says that my expected color was red, but my actual color was green. Well, that's backwards. My expected color is green. My actual color, because of this bug, is red. The reason the error message is backwards is because I put the arguments out of order. And so the error message misleads me. So just convention that expected needs to come before actual. Because now when I run this, you'll see that, expected color, excuse me. Now when I run this, you'll see that my test still fails, but the error message is correct now. It says the expected color was green, but I actually got the color red, which is more accurate. So let me once again try to shrink this back to the usual size. There we go. So just expected comes before actual. And by the way, this code is already uploaded. So you can follow along on the actual code. Again, once I fix this issue, I still have one test failing. Hang on, I can't. There we go. I still have one test failing, and that test failing is dispense not empty test. And it's failing specifically because actually my expected number of my number of candies is wrong. And the reason is I have another bug in my code, and that bug is I accidentally forgot to decrement the number of candies in dispense. So I fixed that, and now this test passes. The reason that I left this bug there, if I forget to decrement the number of candies, but in my test, I only test the output. That is, I don't test the side effects. I only test that the method returns the correct thing. This test would pass even though there's a bug. So again, it's not enough with classes, with objects, to just test the output. You have to also test the side effects. It's not enough to just say this returns true, therefore it works. You also have to test that the number of candies correctly changes and that the color stays the same. When I add those tests back in, they fail. But when I fix my bug by uncommenting that line, I actually am successfully decrementing the number of candies when I need to now. Now my test passes. So, when testing with objects, step 1. Make an object, or objects if you need more than one, to test on. Step 2. Put the object into the state you want to test. Step 3. Call the function. Step 4. Make sure output and side effects match expectations. And if the function is void, it has no output, so you don't need to check that, but you still need to always check the side effects. And if no side effects should happen, then you need to test to make sure no side effects do happen. Any questions? Again, this code is already uploaded. All right. So now we've talked about how to test. You now know how to write a JUnit test. You now know how to write a JUnit test with objects. You set up your initial state, such as if I want to test with a non-empty Pez dispenser, I create a Pez dispenser and I load it. This is putting it into the state I want it. I perform the dispense action and check the side effects. So now the question is, how many tests do you need? How many tests is enough? And that's not an easy question to answer. There isn't a definite answer for any... I can't say 3. The answer's 3. No, it's not. Some functions, 3 may be overkill. You may not need 3 tests at all. Some functions, you may need 40 tests. It varies, and it depends on the function. So what we need is a systematic way to say how many tests do we need to write and what tests do we need to write. And that is referred to as a testing strategy. So real quick, just quickly going through the slides. Anatomy of a JUnit test. If this were a JUnit test, you're always going to have your import statements at the top. You need a test tag before every test method. That method needs to be public and void and have a unique name. We then define our inputs. We hard code our inputs and expected output. We execute the code for the actual output. Never hard code your actual output. From there, we have our assert statement. Test result, this is what it looks like when a test fails. Once we fix the problem, it will pass. The bar will be green. There are different assert functions. There's assert true, and it means that whatever this value is equal to true, or the test fails. Assert false, it means whatever this Boolean value is, if it's true, the test fails, passes if it's false. There's also assert array equals, so don't use assert equals for arrays. Assert equals for arrays does not work, but there is assert array equals, and it makes sure that the values, the two arrays, have the same size, and that every value of the arrays are equal. There's assert null. That means that something is equal to null. There's assert not null, which I'm missing a parenthesis there, but that fails if the value is null. There's also this keyword fail that makes the test automatically fail. There is not one for pass. So a test fails if any one of the assert statements fails. If one failure occurs, the whole test fails. The test passes if we reach this closing bracket without having failed. So you can think of this like an obstacle course. You pass the obstacle course if you get through all three of these. It's like American Ninja Warrior. Or Sasuke is actually how I think of it, because I was watching Sasuke back on G4 before there was American Ninja Warrior. Point is, each of these tests is like an obstacle. And if you get through it, that's fine. But you can't just say, I got through one obstacle, the test passes. You have to get through all of them. And if you reach the end of the course without having failed on any obstacle, then the test passes. That's why we don't have a pass keyword, but you could have something like an if statement, and one of the branches of the if statement is fail, and that would be a way to make sure the test fails if you reach that line of code. Also, when you're doing assert equals with objects, like we do here with color, these colors are objects. It runs that objects equals method. So for instance, if I said two Pez dispensers were equal, it would run the Pez dispenser equals function. Or if you asserted two photographs were equal, it would run the photographs equals function. By the way, quick clarification, I'm not expecting you to do JUnit on homework 1, but you will have to do JUnit on homework 2. But you are not expected to do JUnit on homework 1. Any last questions about the mechanics of JUnit? Oh, the last one. Assert equals with doubles. This is a bit weird. Assert equals doesn't work great with doubles, and it's because of that mathematical imprecision. We've talked before about how, and I'll just write this as a test real quick. Public void double demo. Double R equals 2.0. If I say assert equals, I can't come up with a good error message, so for now I'll write error message. On the homework, you are required to write good error messages. R, comma, math dot square root R times math dot square root R. This test fails. And the reason this test fails is if you look at the value, it actually is going to give you an error message saying something about deprecated. And this is because if you actually were to print system.out.println math.square root R times math.square root R, it's not 2. It's 2.00004. And that does not equal 2. So with doubles, you have to allow for a certain tolerance factor. That tolerance means if the answer is within if the answer is within that tolerance of each other, such as within one, and this would be 1/10,000th. If the two numbers are within 1/10,000th of each other, then the test passes. So this first test passes because 2 and 2.00004 are within 1/10,000th of each other. These two numbers are 4/10,000ths apart. Therefore, they're not within the tolerance, so this test would fail. There is no globally correct tolerance value. It depends on the situation. For example, if I'm doing mathematics, I may want my tolerance to be even less than 1/10,000th. But let's say I were simulating the solar system. If I were simulating the solar system, let's say I was within 100 meters of correct, that's good enough because the solar system is so big that 100 meters means nothing. It absolutely means nothing. But if I'm trying to program an elevator to go and stop on a given floor, being within 100 meters is not good enough because that could be the difference between me stopping on the first floor or me stopping at the penthouse. 100 meters is a huge difference in that context. So your tolerance value will depend on the situation. This only exists when comparing doubles, and it's because doubles have that imprecision we've talked about. Any questions? You guys are quiet today. All right, so we're going to take our break. I don't have a problem to work with you on over the break. We are going to take a break. I encourage you to download from Colab. I encourage you to download Pez Dispenser and Pez Test, which is what I was working with. And using the test that I gave you, try to debug Pez Dispenser, which granted I've already done for you, but it's good practice to make sure you're getting JUnit set up. Keep in mind, though, that what you will want to do with the Pez test, if you just click and drag it in, you're going to find that you'll probably get an error. You need to add JUnit to the build path. So what you need to do in any project where you're going to do JUnit testing is, again, just right-click on source, go to new, JUnit test case, and then you can just make a dummy one. Just call it dummy. But then when you go to create it, it will ask if you want to add JUnit 4 to the build path. Make sure you have JUnit 4 selected, and then you can do that. So try to get JUnit 4 set up. Try to get Pez Dispenser and Pez Test going, and then try to fix the bugs in Pez Dispenser.java. And that's all on Colab at the moment. So we'll come back from the break here in about 9 minutes, and we'll proceed with the rest of the material for today. Be right back. We'll be back at 18 after. right, welcome back, everyone. Just give me 1 sec. There we go. Okay. We're back. So, now that we've talked about how JUnit works at a mechanical level, let's talk about how to use it. We're going to talk about testing strategy. So before the break, it says last time because typically this was 2 different lectures. Before the break, we talked about how we have testing scenarios, input, expected, output, and actual output. How we have this assert equals, message, expected, actual. Message is an error message to print if the test fails. Expected is what we expect the program to output, which we hard code. And the actual is the actual output from running the code. We talked about these different assert methods. So now, and actually we talked about testing with objects and testing side effects. These slides already uploaded. You can revisit them on your own. So the question is, how many tests is enough? Well, so let's think about this. How should we test the load and dispense function? Do we need to test load on a full Pez dispenser? It might actually be worth testing. It could be possible that we have it where our load function would pass if the Pez dispenser were empty, or that the load function would pass if the Pez dispenser were full, but that code could have a variance. So it may be worth testing both cases, where the Pez dispenser is initially empty, or where it's full, or where it's partially full. So really all 3 cases. Do we need to test dispense on partially full? Sure. Do we need to test dispense when there's only 1 test left? Yeah, that makes sense. Now that said, if I test dispense when my Pez dispenser has 6 candies. So let's say I test dispense where Pez dispenser has 6 candies. Do I also need to test dispense where Pez dispenser only has 5 candies? Not really. Because if I'm going from 6 to 5, I would expect that behavior to be the same as when I'm going from 5 to 4. So in theory, could you write 13 tests for dispense? 1 with 12 candies, 1 with 11, 1 with 10, 9, 8, all the way down to 1 plus 0. I could do that, but is that a practical use of my time? No. So the question is not how many tests would be ideal to write. Because sure, you should write as many tests as you reasonably can. But realistically, you can't write tests for every possible input. So instead, what we need is we need to have a plan, a strategy, to decide what tests to create. So a test plan is not about writing individual tests. It is about deciding which tests to write while you're building the system. There is no perfect number of tests. So some strategies would be, for instance, exhaustive testing. But exhaustive testing is just not feasible. Take, for example, the function... Take, for example, the function max. I have 3 inputs. Well, each of these ints can be any one of 2 to the power of 32 ints. That means that if I wanted to test every possible input, I would need 2 to the power of 32 cubed, or 2 to the power of 96. This is a really, 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 really big number. So it would be much larger than all the computing resources in the world. So we cannot test exhaustively even a simple function like max. So we shouldn't try to test exhaustively. But what we should do is think about how we can test effectively. To that end, we have 2 broad strategies. There's black box testing and there's white box testing. Black box testing is writing tests based on the specification of the code. That is, look at the specification and let the specification tell you what tests to write. It does not tell you what individual tests should output. That's on us. We write the individual tests. But deciding which group of inputs to use, that is decided based on the specification. White box testing, however, is actually designing tests based on our code. And we're going to do a brief example of this. So, black box testing, exhaustive testing is an example of black box. We test every possible input based on the specification, not feasible. We could do random testing where we randomly select inputs, but that also isn't feasible because we might miss particularly interesting test cases. For instance, if I picked random numbers, random integers, what are the odds that I'm going to create a test case where all three of the inputs are equal? They're very, very small. So instead, we want to do this thing called equivalence partitioning, and that sounds scary. But what that is planning ahead and deciding what groups of inputs behave largely the same, and make sure to test each of those groups one time. For example, let's say we were testing the function absolute value. The absolute value takes in one input. We'll call that x. That x has three groups that are interesting, that behave differently. For example, there is positive integers, and I'm going to say integers, so that's from 1 to, dot, dot, dot. It's effectively infinity, but, as we talked about, there's a cap on int. But for now, positive. And that's different because it behaves differently than negative numbers. We have negative numbers, and those behave differently than positive because the absolute value of a negative number, you change the sign to be positive. And then we have 0, which is an interesting border case. It borders between positive and negative. So if I were testing an absolute value function, I would write 3 tests. One with a positive number, one with a negative number, and one with 0. That's what we mean by equivalence partitioning. And when we do black box testing, we are writing the test as though we have not coded the solution yet, because it turns out we can do just that. And this leads us to talking about test-driven development. So test-driven development is writing tests before we write the code. And this is because our tests don't rely on the code, they only rely on the specification. So we can do this. We can write tests for a problem before we write the actual code that implements the test. And you may think, well, why would we do this? You probably are in the habit of you write your code and then you test it. It turns out that test-driven development is actually, and it's been studied to be shown to be more efficient. You will ultimately save time if you do test-driven development. That is, you write the test before you write the code. It encourages you to write highly cohesive, loosely coupled code. And I know you don't know what that means yet, but it's a good thing. The unit tests are a way to formalize in your mind what the function should be doing. And it enables you to rapidly correct bugs, because as soon as you introduce the bug and run the test, you'll notice it fails. You can fix it immediately. So we're going to do a test-driven development exercise. And let's start with this example. Let's say we're writing a function called calculateBill that takes in 3 inputs: a number of courses you are taking, an amount that you are overdue, that is, amount that you owe already before the bill is calculated, and then a boolean whether or not you are exempt from interest. So, the function works as follows. First, you pay per course that you take. But, at this made-up university where this bill is being calculated, if you take less than 3 courses, so 1 or 2, you have to pay $8,000 a course. If you take between 3 and 6 courses, you have to pay $6,000. And if you take more than 6 courses, you pay $5,500 per course. So you get kind of a bulk discount. Now, if you already owe more than $2,000, you have to pay 10% more for the courses. Further, if you are not exempt from interest, then the amount that you're owed also increases by 10%. If exempt is true, the penalty is waived, the overdue amount does not change. And the bill is the total of whatever your courses are, whether or not you add that 10% depending on how much is overdue, and then it's the total of overdue and total. It's the sum of those two values. From here, I can already design test cases. But first, before I do that, I'm going to write a stub. So let's go ahead and create a class. I actually already have this written. I'm going to write a stub for my calculate bills method. My stub is going to take in courses, overdue, exempt, but it's simply just going to return 0.0. This is a dummy value. And for now, I'm going to hide the implementation. We haven't written it yet. This is called a stub, and it's a stub because we wrote the method such that things that call this method will compile, but when we run it, it's not yet implemented. So this code compiles, we can call it, it just doesn't work yet. That's how we start with test-driven development. We write the stub. From there, we can then write tests. And we design our tests first by thinking about how we can cover each partition. So we want to select test cases such that every meaningful partition is meaningfully covered. Because this function is a stub, our tests will initially fail. But that's okay. We're okay with our test failing at first. We're then going to implement our function so that the tests pass. So, obviously we're not going to test every combination of ints and doubles and Boolean. That'd be 2 to the 97 possibilities. That's too much. But here's a question. If we test with a test case that has 4 courses, do we also need to test with 5, given our specification? No, because both of these fill the same bucket. We don't need to test both 4 and 5 separately. Similarly, if we test with 8 credits, do we also need to test with 10? No, because once again, they're in the same bucket. And if we test with overdue is 2,500, do we also need to test with overdue 3,000? No, because once again, they're in the same bucket. So we don't need to test all the possible inputs, but we do want to test each of these buckets. And so from there, if I were to list my buckets, I have number of courses, 1 and 2, 3 through 6, and greater than, I should say greater than or equal to 7. My overdue amount, I have 2 interesting partitions based on the specification. It says increased total of overdue is greater than 2,000. That leaves me with these 2 groups. Overdue less than or equal to 2,000, and overdue greater than 2,000. And then exempt is a Boolean, so I have 2 buckets for that, true and false. Right? So, you could think of each of these buckets, I want 1 test covering each of them. Otherwise, I have a partition that's untested. But I don't need 12 tests. I don't need 3 times 2 times 2. I only need to cover each partition once. I'm not saying I need to cover every combination of partitions, just each partition one time. So I can start as a bare minimum with 3 tests, because this bucket has 3, or this group has 3 buckets, the other buckets only have 2. So I could design a test case like this, and I've color coded it to try to clarify each group. I have 1 through 2, that's covered by test case 1. 3 to 6, covered by test case 2. Greater than 7, covered by test case 3. I have less than or equal to 2,000, covered by test case 2. Greater than 2,000, covered by test case 1 and 3. I have true for exempt, covered by test case 2, and false by test case 1 and 3. And before I implement my code, I can do some hand calculation, and I can find these actual. I'm going to do one example for you of how I calculate by hand. So let's say I were doing my test case is 2, 2,500, and false. Let's look at the specification to figure out what our expected should be. Because we have only 2 courses, it's 8,000 per course. So 8,000 times 2, that is total equals 2 times 8,000 equals 16,000. I need to increase the total by 10% because my overdue is greater than 2,000. So this plus 10% is the same as 16,000 plus 1,600, which is 1,760. So this is my total. Similarly, exempt is false, and so I need to increase the overdue amount by 10%. So that means my overdue amount is 2,500 plus 250. That's 10%. Equals 2,750. This is my overdue. From there, total plus overdue, that is going to be 0, 5, 6 plus 7 is 3, carry the 1. 7 plus 2 plus 1 is 0, carry the 1, 2. So 20,350. That is the bill. And if you look at my table, that is what I wrote down. So I can calculate based on these inputs, which I designed by equivalence partitioning, I can calculate the expected. I have not implemented the code yet. The code is still not implemented. And that's because my goal is to design the test case before I try to implement the code. I can then immediately go and write all of these tests in JUnit. So here are my tests in JUnit that match up with the slides. Notice that on the slides, I have 3 test cases, 1, 2, and 3. And on build test, which is uploaded on Colab, I have test 1, test 2, and test 3. And these match up. If you look at the inputs, they match up with the slide exactly. Look at my expected outputs. 20,350, which matches up with 20,350, 31,500, 31,500, 51,150, 51,150. The test cases have the same input. They have the same expected. I'm setting my tolerance to say if the answer is within 1 cent, if the values are within 1 cent of each other, then I'm happy. Because this is a double, so I do need a tolerance value. From there, I can get my actual with bill.calculateBill, except at the moment, all of my tests will fail. And all of my tests will fail because I have not implemented the bill function yet. But this is the first step of test-driven development, writing the tests. Are there any questions about how I arrived at these tests, how I designed them, or how they are implemented? I'll give a minute for people to ask questions. So everyone understands how I designed these tests. What it made me design my tests with these inputs. That was black box testing. Black box testing told me which inputs to select, that equivalence partitioning technique. I then calculate by hand the expected value, but I don't have the actual because I haven't implemented it yet. You guys are quiet today. This is kind of unusual. It's a little bit unnerving almost for me. Anyone there? I'm so lonely. No. All right. So from there, let's say that I implement bill.test, or not bill.test, excuse me. I implement the calculate bill function as follows. Let's say this were my implementation. Now, it's hard to just look at this and tell whether or not it's correct. There's a lot of code here. But I've implemented this. Now let me run my tests. So I'm going to run the tests that I wrote based on this implementation. Again, I wrote the test before I wrote the implementation. And I run, and you'll see that all 3 of my tests pass. So once I have all 3 of these tests passing, then I have completed my test-driven development process. Does this mean that my code has no bugs? And I will wait until people type. Does this mean that because my 3 tests that I wrote beforehand pass, that this code has no bugs? Not rhetorical. I will wait till people type an answer. No, very good. It doesn't. And in fact, this code does have bugs. And we're going to talk about how we can find them now. Because so far, what we have been doing is black box testing. We designed our tests, our inputs. Because remember, these strategies are not about how the test is written. It's about selecting which inputs to use. And so far, we've done that off black box testing. But it's possible that there is some unique combination of partitions that we missed. So how can we check that? Well, what we can do now is we can look and use white box testing. What do I mean by that? White box testing takes into account how much of our code we have tested. So white box is called white box because we have to, and sometimes you'll see it called glass box testing. I think of it as black box, where you can't see the code. White box, you can see the code. And white box testing is done through the use of developer tools. I want you to notice in Eclipse, and I'm going to blow up Eclipse again. Anytime I've run my code, I've been hitting this run button, like so. But there's some other run buttons. For example, there's this run with debugger, and if you're familiar with how to use debugger, you can use that. But there's next to the run button, there's this run, and if you hover over it, it says something called coverage. And I'm going to click that. And when I run coverage, the colors, Duke, the colors. And no, you won't get that, I'm old. But I get a bunch of cool colors. What do these colors mean? Well, these colors have a particular set of meanings. Green and yellow. At least one test executed that line of code. Red. No tests executed that line of code. Again, you get this not through the run button, but to the right of it, it's like run with a little bar. It's run with coverage, and it will do this color coding. Now, we should never submit lines of code that haven't been tested. Should never submit code that you haven't tested. So, let's think about how we can design a test such that we execute our 2 lines of code that haven't been executed, our 2 lines of code that are red. Let's try to design test cases so we execute those lines. The first one, you'll notice, is, let's take a look at this line of code, the one on the bottom here. This is total overdue, total plus overdue times 1.1, line 25. You'll notice that that line is red. So how can we design a test case to get there? Well, we can look at the code and we can kind of backtrace and see, okay, in order for me to hit this else, both this else if and this if condition need to be false. So I need both this condition to be false, that is overdue less than or equal to 2,000, and exempt to be false. Or I should say either of these need to be true. And then also overdue greater than 2,000 must be false. So that means overdue must be less than or equal to 2,000, and exempt needs to be false. That's the only way that I can reach this line of code. And if you'll look, none of my existing test cases cover that. I don't have anywhere where overdue is less than 2,000 and exempt is false. The only test case where overdue is less than 2,000, exempt is true. So we design another test case, test case 4, and we're going to say, okay, if we don't really care how many courses we have, let's say 5, but we know exempt needs to be false, so let's set that. And we know overdue needs to be less than 2,000, so let's set that. So I picked these 3 inputs, 5, 1,500, and false. So I'm going to write a new test. Test 4. 5, 1,500, and false. I then calculate by hand my expected value, which I've already done here as 31,650. So 31,650. My tolerance doesn't change. The way I get actual doesn't change. I'm going to say test with 5 courses, 1,500 overdue, and non-exempt false. I don't know why it says failees. That's not intended. I then run this test. And alright, this test passes. So even though I didn't test this scenario, it still works. My code was still correct. But now when I run with coverage, you'll see that now this line is green. So we have now tested this line of code successfully. Are there any questions about what I just did here? Again, the idea was I didn't have any tests that executed this line of code. I designed a test to execute that line of code, and that test passed. So I'm happy. Any questions about that? Okay. So now let's look at the last line of code that we haven't tested. Specifically this one. Line 20. How do we get here? Well, we get here if this statement is false, which means either overdue is less than 2,000 or exempt is false. But then because of this else if, overdue greater than 2,000, if exempt. These are kind of the 2 direct guards. This means that overdue must be greater than 2,000 and exempt must be true in order to reach this line of code. Let's take a look at our tests and see if we have that. Obviously, test 4 doesn't have that. It's neither over 2,000 nor exempt is true. We look at our 3 previous tests, and where overdue was over 2,000, we said false. So we have not tested over 2,000 and true. So let's design a test case. Let's design a test case, 5 courses, overdue over 2,000 and exempt is true, and see if our code passes. So I'm going to come up with test 5. I'm going to leave courses the same because I don't care. I'm going to say overdue is 2,500, greater than 2,000. And I'm going to say exempt is true. I update my error message. And exempt true. From there, I have this input. I calculate by hand what would the bill be. And the bill would be, which I've already calculated ahead of time, 35,500, excuse me. 35,500. So I write that in. 35,500. And now I run my test. And notice that this test fails. And the reason this test fails is because this line of code is actually a bug. It's incorrect. If you read the specification, it says, if more than 2,000 is overdue, then multiply total by 1.1. That is, increase total by 10%. But if they are exempt, do not increase overdue. If you'll notice, my issue here is I'm multiplying 1.1 on the wrong value. It should be total times 1.1 plus overdue, not overdue times 1.1 plus total. So I'm going to move this 0.1. And then I'm going to check if that fixes the bug by running my tests. And now all of my tests pass. So because I hadn't executed this line of code, I wrote a test. And I'm calling this 5A because this was our test before we fixed the bug. I ran the code and my actual did not match my expected. I realized that this was because it was a bug, and so I fixed the bug. I changed that line of code, and I reran the same test. So this is still test 5. I didn't change it. I'm just calling it 5B because it's the second time we run it. And now the test passes. Now we have 100% statement coverage. When I run my build tests with coverage, you'll see that every line of code is either green or yellow. There is a difference between green and yellow I'll talk about in a second. But this means we now have completed white box testing. We have tested all of this function. So does everyone understand the difference between how we do black box testing and how we do white box testing? Are there any questions about the difference? Remember, it's no different how we write the tests. The tests are written the same way. It's how we select what inputs to use. Just in question, could we state fields outside of the test tolerance variable? So variables should only be created in the test they are used. That said, if you want there to be a constant tolerance value, you could define it in the global scope, but you just have to be very, very careful to never change it. Because if you change a global variable in a test, it will break all the other tests. And there are ways to use this tag called before, which certainly you're welcome to use if you want to look into. I'm not going to get into for the sake of time. So the question then you might be thinking is, which should we do? Are we required to do black box testing or white box testing? And to that end, I say... Hang on. One second. To that end, I say... Oh, come on. Why not both? You do black box testing by writing your function tests, writing your designing your test before you write the function. After you are done writing, if you find there is code that you have written that has not been properly tested, then you should, and I wish it would show the draft in the static. It only shows it when I'm in the display setting. So that's kind of sad. Oh, it's not showing up here either. That's weird. There we go. I'm sure you already explained this. What's the main difference between this type of testing and main testing? So you can do black box testing and white box testing in main testing. There's nothing preventing you from doing that. The downside of doing main testing is it means that you are combining testing your program with running your program. Because sometimes you'll run a program with the main method designed to do something. Your main method will have a specific purpose. And if your tests are also in main, that means that before you release your program, you have to comment out all your tests. By using JUnit tests, it makes our tests kind of separate from main. It also makes it where the tests will automatically tell us whether or not they pass. So for example, on WebCat, I'm actually, well, not me, but WebCat is running JUnit tests that I wrote. And that is automatically detecting passes and fails to give you a grade. So main and JUnit testing are kind of opposed, and you should generally do JUnit testing. But on homework 1, do main testing. It's fine. You don't need to do that yet. But homework 2, you're required to do JUnit testing. Black box and white box are how you pick which inputs to test on. Does the, forgive me, it censored that, and I think it may have been because you put a dot in there. So the test has to be in the same folder in Eclipse. If you're using IntelliJ, it may be a bit different. But notice that my test file is in the same folder as Bill. So I have Bill and I have Bill test. And by the way, on the class website, I have Bill and Bill test. That's my starting point. Then I have Bill final and Bill test final. That was my ending point. So I've already uploaded my ending point as well as my starting point. So the two files with final in the name, that's where we ended at the end of class. Test Java file. Yeah, so I have, here they are. Bill and Bill test are in the same folder. Otherwise, you have to do an import statement. But also, you need to add, you have to have a JUnit, you have to add JUnit 4 to the build path. And if it's not there, you can add it to the build path just by doing something like new JUnit test case, and then just like call it temp or whatever. Make sure you have JUnit 4 selected, and when it prompts you to add JUnit 4 to the path, you say yes, and then you can just delete temp, and JUnit 4 will stay in the path. You should see this in your folder, JUnit 4. Let me enhance here. You should see this JUnit 4 in your project folder. If you don't, you need to add it to the path. Which, again, you can do that by just making a dummy JUnit 4 test case and then deleting it. Any other questions? Alright, so I'm going to get started on the next topic. I'm going to open up a slide deck here. Software development life cycle. And while that's opening, just give me 1 second. Here we go. Oops, I have still... There we go. So today, we're going to start, and we'll finish tomorrow, because I won't get through all these slides. There's unfortunately no cool coding. This is all just going to be slide information. But we're going to talk about the overall process of building software. And again, these slides supplement the textbook. You should do the reading. Remember, this is the textbook that is available online. The link is in the syllabus. So... And these announcements don't matter. I need to delete them. Don't worry. But not sure why. All right. Anyway. So one of the things that we need to worry about when we're building software is making sure that we're actually building what the customer wants. This is a real problem. I talked yesterday about how many software projects fail. If you remember, I showed you this graph, which showed how the norm for software is for the project to be over budget or late or missing key features or some combination of all three. That is normal. How do we avoid that? That's the question. How do we make sure we're building what the customer wants? Well, first, let's define, when we're talking about software engineering, we're really talking about building big programs. Real quick, just a rough estimate of lines of code. What's the largest program anyone in here has written? Rough estimate, lines of code. Okay, 1,100. 1,500. All right. Anyone top that? Anyone above? Has anyone here written code that is over 2,000 lines? What about 5,000? What about 2,000 or more? There's a unit for measuring the size of a program that is KLOC, which is thousands of lines of code. And the fact that that is a common unit should tell you that programs can get very large. How many classes is your largest program? Homework 1 only had 2 classes. What if you had more than 20? More than 100? I've seen that. How do you do that? What is a big program? Well, it may be something like this. Trivial could be one programmer working on something that's, say, less than 500 lines of code, working over a week. But when you get to extremely large programs, and here we're talking about like really large software, like the Android or the iOS operating system or Windows operating system, we're talking about potentially 200 plus programmers working over years on millions of lines of code. And it's important to understand that the techniques that you use to build this, or even this, simply do not apply to building large-scale programs. And this is important because software is all around us, yet software fails frequently. Could you go through a day without interacting with any software systems? Now you may be thinking, yeah, I could put my phone away for a day. You have software system running the air conditioning in your house, if assuming you have that. If you don't, I apologize, because I know it is hot right now. There's software that runs my refrigerator. My alarm clock has software. Also, and this is important, it's not just you using the software. How food gets distributed is entirely based on software. We are so reliant on software for grocery stores to maintain their stocking. There's a calculation that was done, and what it was found was, and this is one of those like, the world may be ending soon kind of studies. So it's depressing. So I warn you of that in advance. What it estimated was that if 3 nuclear weapons detonated in the upper atmosphere or on the surface in the United States, 3 modern nuclear weapons, evenly distributed across the contiguous 48 states, you would basically see, even not counting the death and the radiation, you would basically see about 80 to 90% of the population die. Not even from the explosion or the radiation, but from things like starvation or lack of health care. And that's because the nuclear weapon would take out the power grids of the entire country. And so while there would be food in Iowa potentially, again, even if these detonate in the upper atmosphere, we're not talking about blowing up huge craters. There'd be food rotting in warehouses in Iowa while people were starving to death in Texas because no one would know to get the food there in time because Texas wouldn't have a way to communicate with Iowa to say, hey, we need this food. Because all that communication is done through electronic software. Air traffic control systems, entirely dependent on software. Vehicles, anti-lock braking system, entirely dependent on software. So how many of you, given this horror story I just laid out, how many of you actually believe you could go throughout your entire day without software? Without anyone having software? I guess you wouldn't have to worry about this class anymore, but that's the point. Software is all around us, and that makes failures expensive. For example, the Ariane 5 rocket launch blew up entirely because of a software glitch. Because the software had not been tested in a high G environment. That is a high gravitational force environment. When you're accelerating upward, Newton's third law produces a downward effect that feels like enhanced gravity. There's also Therac 25. Therac 25 was a radiation therapy machine. Due to a bad user interface, strictly just a bad user interface, 3 people died. And 6 people total were exposed to unhealthy doses of radiation. Several times more than was prescribed. And this takes us to this term, the software crisis. The software crisis is a term coined in 1968. And I want to be very clear. The software crisis is not a period in time. The software crisis is just a fact that we are still dealing with as software engineers. And that is that hardware growth has completely outstripped our software development ability. Moore's Law has continued unabated for decades. Only now are we starting to run into real problems with Moore's Law because we're starting to run up against physical barriers we can't cross. With the computers the way they are designed, we cannot represent a transistor any smaller than n number of atoms. We don't know what n is yet, but there is some n, and once we reach that point, with computers as they are, we cannot make transistors any smaller. Now, there is quantum computing, but that's not, trust me, that's not something, you're not going to buy a quantum computer off the shelf in 10 years. It's just not going to happen. Don't think that. But we are, so Moore's Law is ending. But the fact is, Moore's Law continued unabated for a really long time. Our hardware is insane. When I was growing up, we had an NES. Now, the PS5 is coming out, and the graphics are beyond anything my 10-year-old mind looking at the Nintendo 64 ads could imagine. I looked at Nintendo 64 ads. I looked at GoldenEye as a kid and was blown away by the graphics. Go look up videos of GoldenEye and tell me that you're blown away by the graphics now. But I had never seen anything like it. My 10-year-old mind was shocked. The point is, that hardware growth has been continuous. But software has not grown at the same rate. The efficiency of producing software has not continued to grow at the same rate. And the problem is, when you look at Department of Defense projects, they did a study on this. Department of Defense projects, 47% of the software that was delivered to Department of Defense could not be used at all. Just was not useful. They couldn't integrate it. 29% of funded software never delivered at all. So we're already talking nearly 80%. Nearly 80% that just basically didn't meet any requirements and never got used. 80%! Now that was in 1968, but still, 80%! No value at all. And of the remaining 24%, 19%, so 80% of that actually got worked, required extensive rework and it costs 36 times more than the budget to fix the problems after release than it would have to fix them before release. So the point is that we've actually gotten a lot better than this, but this software problem that I talked about, this graph is not new at all. This is not because of the internet age. If anything, the internet has actually helped considerably after the dot-com boom and burst. So, I want to throw this definition of software engineering at you, because software engineering is not a synonym of programming. Software engineering is the technological and managerial discipline concerned with the systematic production and maintenance of software products that are developed and modified on time and within cost estimates. And I want to emphasize, it's not just the production, it's the maintenance. Once you release software, you are not done. That is especially true in the internet age. So software engineering is about thinking about the engineering of the system, building particularly large software systems. This is not just quick and dirty hacks. It's about modifying the system over time to meet new demands. Programming is a part of software engineering, but it is such a narrow fragment. Here's a way to think about software engineering. You have a small creek. You want to cross it. How do you cross this creek? Not rhetorical. How would you cross this creek without your feet getting wet? Jump. Okay, that's one. Just jump across. Any other ideas? That works. You could just jump across it. Build a bridge? Okay, how would you build a bridge? Describe in detail how you would build a bridge. Find a log. There we go. Look, there's a log right here. There's a log right there. I can just walk across that, right? Just find a log, lay it across, and then walk across the log. Right? That's how you could cross that. Okay, how would you cross this? How would you cross this? Jump, exactly. You would jump. Maybe you just find a really, really, really big log, right? Just a really big log. The point being, building a bridge across this creek has the skills that it takes to do this. Has no bearing. Does not help you at all. Build a bridge across this. These are just the scale, because the same problem has been scaled up. The solutions to the small have no bearing to the solutions on the large. And that's the key. Early bridges were like this. This is what early bridges looked like. The people who built these bridges could not build these bridges. It took us a long time and a lot of understanding of science, materials, aerodynamics, all of these to go from here to here. It was physically possible. It was always physically possible to build this bridge. It was always physically possible. It just was a lack of knowledge. That was the key. A lack of knowledge. We didn't know how to refine steel. We didn't know the physics of how to build a suspension bridge. We didn't know what shape to assemble this, how high it needs to be, how long the cables need to be, etc. We didn't have the mathematics or the material science. But if we had those, there's nothing stopping you from building this. And that's the key, knowledge. I mean, and you hear this phrase a lot, knowledge is power. But it really is. However, sometimes that knowledge comes at a cost. This is the Tacoma Narrows Bridge, and if you Google Tacoma Narrows Bridge, you will typically see videos like this, or pictures like this, or that, or here. The Tacoma Narrows Bridge was a suspension bridge, similar in structure and function to the Golden Gate Bridge. But because it didn't take into account aerodynamics, which at the time were not particularly well understood, static aerodynamics simply was not very well understood when this bridge was built. Eventually, the bridge started twisting. Suspension bridges, by the way, they can bounce. This is fine, and they can sway. This is fine. But twisting is bad. And the Tacoma Narrows Bridge would start twisting, and eventually it just ripped itself apart from the twisting. That was because of a lack of knowledge. That's to say that anytime you do have a failure in engineering, it is worth dissecting that failure. And that is exactly what Fred Brooks did. So I would encourage you, if you ever get the chance, to read The Mythical Man Month, and I will type that out. The mythical... Actually, it had nothing to do with resonance frequency. That's a misunderstanding. Resonance frequency was not the problem. It is a common misconception, but it is a misconception all the same. The Mythical Man Month. And Man Month in this case would be more accurately described these days as Person Month. This is the more modern term. But it just means to say that you can think of a man month as a unit of measure. One programmer working 1 month. But one person month is not a predictable unit of measure. Yeah, the physics teachers in high school say a lot of incorrect things. It wasn't resonance frequency. It was torsion. It's the fact that suspension bridges really aren't designed to do this. The reason the bridge was doing this was because of aerofluxing, and you can look at that. It basically turned the bridge into a wing. Anyway. Alright, anyway, I would encourage you to read this. I'm going to cut it off here today, because we're at 3:16. Apologies for going 1 minute over. We will pick up the rest of these slides tomorrow, and then start talking about inheritance structures. So I will see everyone tomorrow. Until then, take care.